Nobody knew why one ship could break the Arctic when thousands failed. No engine roar. No visible struggle. Just 30,000 tons of steel climbing over ice like it wasn't even there. What's hidden inside this monster? By the end of this video, you'll understand the machine that conquered the top of the world. Before you watch full story, comment below from which country are you watching. Don't forget to subscribe for more amazing stories. For thousands of years, humanity looked at the North Pole as a place no one could ever reach. Endless ice, brutal cold, and a force of nature capable of stopping even the mightiest ships in their tracks. But today, one class of vessel does what was once considered impossible. It pushes through terrain that turns ordinary ships into helpless steel wrecks. It carves a path through ice fields several meters thick and reaches one of the most inaccessible points on the entire planet. And yet the strangest part is this: almost no one outside the program understands what actually gives it that power. Why can one ship defy the Arctic when thousands of others have failed? For decades, engineers chased a single question: how do you build a machine that can operate where nature itself writes the rules? Then a ship arrived that changed everything we thought we knew. But its story is far more complicated than it looks on the surface. Behind this giant lies a decade of experiments, dangerous trials, and decisions that could have altered the fate of an entire region. This is the story of a machine that dared to challenge the ice, and a technology that may reshape the future of the whole world. Look at the bow of a nuclear icebreaker and your first instinct is to think of a blade, something sharp enough to slice through ice like a knife through butter. But try cutting a solid slab 3 meters thick with a knife, and the blade simply jams on first contact. A conventional ship slices through water with a sharp, wedge-shaped stem. But the moment that same wedge meets solid Arctic ice, it becomes a trap. It wedges itself into the mass, forces the ice apart sideways, and instantly kills its own momentum. Engineers learned the hard way that ramming ice head-on is the fastest way to strand a ship forever. The secret of the atomic giant lies in a completely different kind of physics. Its bow isn't a blade, it's shaped like an enormous tilted spoon, sloped at roughly 30 degrees. The ship doesn't attack the ice wall, it climbs on top of it. Ice is reasonably good at resisting compression, but it is terrible at resisting bending. When 30,000 tons of steel creep up onto the edge of an ice field, the sheer weight of the hull starts breaking the slab from below, exactly the way a heavy weight dropped onto the edge of a pane of glass shatters it from underneath. The rounded hull form spreads that load so the resulting crack races out ahead of the ship, splitting the ice into manageable blocks before the hull even reaches them. This looks almost beautiful during real Arctic transits. During one especially difficult crossing through heavy multi-year ice, the captain steered the giant straight at a ridge more than 4 meters thick. Slowly, the bow rose up over the white wall. The steel groaned as it absorbed the vessel's full weight, and within seconds, a low rumble rolled out from beneath the hull. A multi-ton block of ice cracked like a dry branch, splitting into huge fragments and clearing the way forward. But the instant the bow climbs onto the ice, a second, far more dangerous trap appears. The massive steel hull can simply freeze in place and lose all forward motion. You might assume ice is smooth and slippery, but at -40 degrees, everything changes. In extreme cold, snow and the top crust of the ice turn into something closer to sandpaper, with an enormous coefficient of friction. When the ship's rounded steel sides press into an ice channel, 1,000 tons of compressed mass grips the hull from both sides like a giant vice. If the ship stops moving for even a second inside that grip, friction alone can lock it in place completely, and no engine, however powerful, will be able to move it again. To defeat this invisible enemy, engineers turned the hull into something closer to a hydrodynamic weapon. Around the underwater section of the bow, powerful nozzles form a pneumatic flushing system. High-pressure pumps blast out a mixture of air and heated water. Millions of bubbles rise along the hull, forming a boiling cushion around the ship. This air and water mixture acts as a lubricant. It stops broken ice fragments from clinging to the smooth protective coating and physically pushes the crushed mass out and away, creating something close to the sensation of sliding on an ice rink. History has recorded just how dangerous lateral ice pressure can be. One famous early icebreaker once got trapped in a brutal Arctic squeeze when ice fields on both sides began closing in around the hull. The air temperature dropped to -45 degrees, and the steel plating groaned under the pressure of hundreds of atmospheres. Only a constant flow of steam and side flushing allowed the crew to gradually reduce friction and break free from the closing jaws of the ice. To tear itself free from ice's grip, a ship like this needs an enormous, instant burst of power, something no diesel engine on Earth can reliably deliver. A diesel-powered ship of comparable size would need entire trainloads of fuel just to reach the high latitudes. Running at full power, a conventional engine burns through hundreds of tons of fuel a day. Supplies run out fast, and refueling in the middle of a frozen ocean simply isn't an option. Worse, ordinary diesel fuel thickens in extreme cold, clogging filters and stalling machinery exactly when it's needed most. An Arctic giant needs an entirely different category of power source, something capable of delivering enormous, sustained force for years without a single refueling stop. At the very center of the ship, behind multiple layers of shielding, sit two nuclear reactors. Their working principle is essentially an incredibly powerful, incredibly reliable kettle. Inside the reactor vessel, the core contains uranium fuel rods. As nuclear fission proceeds under careful control, it releases a staggering amount of heat. Water in the primary loop is heated to hundreds of degrees under enormous pressure, but it's kept from boiling. That superheated water flows into a steam generator, transferring its heat to water in a second, separate loop. That second loop instantly flashes into dry, superheated steam, which rushes at incredible speed onto turbine blades. Those turbines spin powerful generators, which in turn power the propulsion system. This engineering triumph was proven beyond doubt on August 17, 1977, when the nuclear icebreaker Arctica became the first surface ship in history to cut through heavy, multi-year ice and reach exactly 90 degrees north, the geographic North Pole. Its reactors ran in flawless rhythm, producing tens of thousands of horsepower without a single failure, cementing humanity's technological edge over one of nature's harshest environments. But the enormous energy locked inside two nuclear reactors, encased within a single steel hull, creates a brand new threat. How do you cool a red-hot reactor core when the seawater outside is thick with ice? Imagine running a marathon and suddenly having your oxygen supply cut off. That's roughly what happens to a nuclear-powered ship when slush ice invades its cooling system. Running the steam condensers and cooling the primary reactor loop requires an uninterrupted flow of seawater. But as the ship crushes a thick ice sheet ahead of it, billions of tiny ice crystals rush along the hull underneath. That slushy mass gets sucked directly into the intake grates. Within seconds, ice crystals clog the intakes, cutting off the water supply, and temperatures inside the cooling loop start climbing toward dangerous levels. To keep the reactor from suffocating, engineers designed an elegant heat redistribution system. Inside the underwater section of the hull sit special, ice boxes, large internal reservoirs. When the external intake grates clog with ice, automated systems switch the water intake to an internal loop. Hot water from the secondary circuit is pumped, under pressure, back into the intake channels. That surge of near-boiling water instantly breaks apart compressed ice crystals, turning a dangerous blockage into liquid flow again before it ever reaches the sensitive heat exchanger tubing, not unlike the way someone might warm frozen fingers with their own breath. During one particularly dangerous passage, a ship became trapped in what's known as a compression ice jam. Seawater temperature dropped to -2 degrees, and the intake grates completely clogged with slush. Primary loop temperature sensors spiked instantly, threatening an emergency reactor shutdown. The watch engineer immediately switched the system to internal circulation with a steam purge. Within 3 minutes, the slush melted, water flow was restored, and the reactor returned to normal operation. Fighting cooling failures forces the crew to run the pneumatic system and redistribute heat at full intensity, but the vibration from that fight puts brutal stress on the propellers. When a ship reverses or maneuvers through pack ice, its propellers effectively turn into giant meat grinders. Blades slam at high speed into submerged ice ridges, compacted blocks weighing tens of tons apiece. If the blades were made of ordinary bronze, they'd bend or shear off almost instantly. Each impact is comparable to dropping a loaded truck onto a spinning mechanical system. Transmitting a reactor's enormous torque through water filled with solid obstacles is an engineering problem that once seemed unsolvable. The solution: propellers with replaceable blades built from an ultra-high-strength steel composite. Each blade weighs several tons and bolts onto the hub with fasteners engineered to withstand extreme shear loads. Direct-drive electric propulsion motors allow the ship to instantly reverse direction without relying on fragile mechanical gearboxes. When a blade at full speed strikes a submerged wall of multi-year ice, a massive shockwave travels the length of the drive shaft, dozens of meters long. It might seem like that steel shaft should simply twist itself into a corkscrew from the sudden deceleration. To protect the electric motors from a catastrophic shaft failure, the transmission includes hydrodynamic couplings and elastic dampers. These absorb the kinetic shock within a fraction of a second, buying the automated systems just enough time to cut power and protect multi-ton machinery from mechanical destruction. Because electric motors deliver maximum torque even at very low speeds, they can effectively grind ice caught under the stern into fine slush, almost like a kitchen blender. Even these ultra-durable systems sometimes need repairs in the middle of nowhere. During one expedition, the outer blade of the starboard propeller was damaged by unusually hard, old ice. In air temperatures of -30 degrees, the crew carried out a remarkable operation. By shifting ballast, they raised the stern nearly clear of the water and wedged the ship firmly between two dense ice fields. Divers in heavy-duty suits descended to the propeller and, over 6 hours, replaced the multi-ton blade with a new one, restoring the ship to full operational readiness. Even with intact propellers, a ship can still lose all maneuverability if a massive ice ridge locks up its rudder completely. Picture driving into a snowbank and having your wheels spin helplessly. A giant ship in the Arctic can end up in exactly the same situation when it climbs onto a huge ridge and loses momentum. A multi-meter layer of compressed ice slides underneath the hull, and the ship settles onto it under its own full weight, effectively hanging in midair. The propellers keep turning, but the ship goes nowhere, not forward, not backward. Meanwhile, the surrounding ice fields begin closing in, and the ship risks becoming a stationary target for crushing lateral pressure. To break free, the ship activates its healing system, enormous ballast tanks positioned along the sides, bow, and stern. Powerful pumps can shift hundreds of tons of water from the port side to the starboard side within minutes. The ship begins to rock, slowly but relentlessly, first one way, then the other. A steel structure the height of a 5-story building sways back and forth in the ice like a giant weeble. Its sides press with tremendous force against the edges of the ice trapping it, cracking the mass apart and widening the channel around the hull. This method has rescued ships from seemingly hopeless situations more than once. Near a remote Arctic archipelago, one vessel became locked solid in a powerful ice jam during the dead of night. The captain gave the order to activate the healing pumps. Within seconds, tons of water rushed to the starboard side, tilting the ship by several degrees. A tremendous crack rang out, the ice pack under the port side gave way and split apart. One more pumping cycle later, the ship slid free of the ice wedge and back into open water. While the ship rocks and shudders like it's living through a continuous earthquake, and the hull absorbs blow after blow from multi-ton ice blocks, an invisible enemy is building up inside the reactor compartment: vibration and thermal stress. Constant shaking, sudden stops from ridge impacts, and heavy listing can loosen fittings, damage high-temperature piping, or trigger microscopic cracks in steel structures over time. Protecting the reactor can't just mean strong. It has to mean absolute. The reactor's engineered protection consists of several isolated layers. The reactor itself sits inside a sealed steel capsule, surrounded by a thick barrier of specialized concrete containing barium and lead, plus a water buffer layer. The entire assembly rests on powerful hydraulic dampers that absorb outside shocks and vibration from the ship's constant battle with ice. The physics is the same as in a high-performance car's suspension system, just scaled up by a factor of thousands. When the hull slams into a ridge, the fluid inside the hydraulic cylinders absorbs that kinetic energy and dissipates it smoothly, protecting the reactor from even microscopic deformation. Even if the bow itself were badly damaged in a head-on collision, the reactor compartment would remain completely untouched inside its protective cocoon. This protection is tested constantly under the harshest conditions imaginable. During one especially difficult stretch of record-thick ice, the hull absorbed a series of powerful impacts against old ice hidden beneath the surface. Load sensors spiked several times above their normal operating range, and lateral vibration amplitude climbed toward dangerous limits. But the automatic safety systems responded instantly. The hydraulics perfectly absorbed every external shock, preventing any damage to the piping, and radiation monitors both inside and outside the compartment recorded no deviation whatsoever from normal background levels. Having survived every engineering challenge and endured brutal, relentless stress, the Icebreaker finally approaches the point where every line of longitude on Earth converges. As you near the very top of the planet, your compass starts to lose its mind. Magnetic meridians all collapse into a single point. An ordinary compass needle spins erratically, and navigation satellites hover right at the horizon, constantly losing signal to interference. It can feel like navigation itself becomes impossible here. But the deeper paradox is that the ice beneath your feet isn't standing still either. It continuously drifts at several kilometers per hour, shifting every landmark and forcing the crew to recalculate their course every single minute. You can't simply set a heading and lock the wheel, because the ground beneath the ship never stops moving in unpredictable directions. To pinpoint exactly 90 degrees north, the ship relies on a complex of inertial navigation systems. Laser gyroscopes, capable of detecting the faintest rotation of the Earth itself, work in tandem with algorithms that model the drift of the surrounding ice. Spectral sensors continuously track shifts in the ice mass and calculate a precise trajectory accurate to within a matter of centimeters. It's a bit like trying to thread a needle while standing on a platform rocking through a storm. The captain guides the giant ship, centimeter by centimeter, toward the single point on Earth where every direction around you points south. When the target is finally reached, the ship gently drives its bow into a dense, multi-year ice field and deploys special ice anchors to fix its position relative to the shifting mass around it. The onboard systems lock in the precise coordinates, 90 degrees, 0 minutes, 0 seconds north. The enormous atomic giant comes to rest in the middle of an endless white ocean. The crew lowers a gangway onto the 3-meter thick ice, confirming a triumph of engineering over one of nature's most unforgiving forces. Engineers built a machine capable of operating in conditions where human presence once seemed physically impossible. That success proved humanity could hold its own against the Arctic. But as the climate continues to change and even more powerful nuclear icebreakers, like Russia's next-generation Leader-class vessels, begin to enter service, an entirely new era in polar engineering is only just beginning.